But the wavefronts change a little bit, and I'll show a little demo program to show how matter changes the wavefronts. So here's a wavefront from some radiative source, okay? And so we have these wavefronts going through air, for example. And so we track these wavefronts, and here they travel through air, and then they hit this glass over here, or some medium that's transparent. It's just shaded here to indicate it's different. And the result of all that constructive and destructive interference is that the net wavefronts change. They change in two ways. One is the wavelength actually changes. The distance between these successive wavefronts is smaller in the medium than it is out here. Okay. There's a direction change going on, and we can actually see some direction change if we draw these, again, these radial lines are the light rays. We see how the light rays, if we keep drawing them perpendicular to the wavefronts, then the light rays actually bend, at least at certain angles, when they enter into the medium. And the wavefronts are actually traveling slower. A single net peak in the wavefront moves slower inside the medium than it does outside, which brings up an issue about the speed of light. Isn't the speed of light a constant? Isn't the speed of light a universal constant? And doesn't the superposition principle tell us that no matter what we have in the way, the speed of light should be the same? You might have heard that light travels slower in various materials than it does in vacuum. You have to be careful about how you phrase the question. If I have a flashlight, for example, and here is a block of glass, and here's some detector over here where I'm going to detect the light coming in. There's really two ways to measure the speed of light. One is turn on the flashlight at t equals 0, and then measure the time when your detector actually measures light hitting it, and then the speed is going to be this total distance divided by that time. That should give you the speed of light. That should give you 3 times 10 to the 8th meters per second, no matter what's in the way, because the superposition principle tells us that this initial radiation comes through, and even though there's re-radiation, that initial radiation isn't affected by the re-radiation. It's still going to reach the detector at time t equal to d over c. Okay. But if you ask a different question, which is tracking one of these wavefronts, remember these wavefronts are the net wavefronts are the results of not just the incident radiation, but the re-radiation, that's a different question. And you can measure the speed of light differently by saying, how much time does a wavefront take to move through from one point to the other? And so the speed of the wavefront is going to be the wavelength divided by the period, okay, the period of oscillation of one of these sinusoidally oscillating charges. Or we could also write that as lambda times the frequency. And this thing will be different in different media because the wavelength, the distance between wave fronts is going to change. The frequency does not. The frequency doesn't change because these charges are still oscillating at the same frequency. But the wavelength actually changes. Okay? So we want to think about how these wavelengths change in different materials. And transparent materials have a property associated with them that tells you how much the wavelength has changed, and it's called the index of refraction. Index of refraction is given by the symbol little n, which is unfortunate because that's also the same symbol we use for mobility, or electron density, but we'll just have to deal with it. The formal definition of n is the speed of light in vacuum, 3 times 10 to the 8th meters per second, divided by the speed of the wavefront inside the medium, okay, which is different. We see these wavefronts moving slower inside the medium. Okay? But again, because we can compare these two speeds, we can say the speed of light in vacuum is going to be the wavelength in vacuum times the frequency. And the speed of the wavefront is going to be the wavelength inside the medium and when I say the word medium, I just mean some material that the light is traveling through. Okay, so speed in vacuum lambda in vacuum versus lambda in medium times the same frequency. Okay, and the frequency, of course, cancels out, and so you could also use this as comparison or a way to calculate the new wavelength. If you know the wavelength in vacuum and you know the index of refraction of the material, you can calculate the wavelength in this medium. Okay. Now notice it's a pure number because we're dividing a speed by a speed, so we just get a number. And what are sizes of n's? Well, for most ordinary materials, pretty much everything we're going to deal with, n is greater than or equal to 1. Okay? So in vacuum, by definition, n is equal to 1. We just take the speed of light divided by the speed of light. In air, at standard temperature and pressure, n is approximately equal to 1.0029, which is often close enough to 1. Air doesn't really affect the wavefronts that much. Water, n is approximately equal to 1.33. And then various things, you have like plexiglass, for example, or n's about equal to 1.5. And other types of plastics, n's about 1.3 to 1.5, so it depends on the material. But those are some typical values, okay?